Good afternoon, everyone, or good morning for our two panelists. For one of them, it's really early in the morning. For the other one, not that early, but still morning. And as already introduced in yesterday morning in the first part of the panel discussion, we split it in two parts, and we started discussing already yesterday, but today we will get a bit different perspective on the unsolved problems and future directions in intelligent operation and maintenance. And I'm very happy to invite our two panelists today. So the first is Dr. Patrick Bangert, who is currently Vice President in Samsung. But he has a very unique perspective because he did several roles and several stakeholder perspectives. So on the one hand, he has been professor. On the other hand, he did start his own company, but currently he is with a big corporation. So we're very happy that you joined us to give us this particular perspective. And the second panelist is Dr. Daniel Nikovski, who is with the Mitsubishi Electric Research Labs in Cambridge, in US as well, who has been in research and development with Merle for a while and has also continued and has witnessed the growth, but also the development of this domain. So without further ado, I would like to invite first Patrick to introduce shortly himself, but also to introduce again shortly what, from your perspective, the biggest challenges and opportunities are. And then I will give over to Daniel, and afterwards we will open the floor to questions into open discussion.
Yeah, so thank you very much. Thank you very much for inviting me. Hello, everybody. I hope you're having a really great conference. My name is Patrick. I lead the AI division at Samsung SDS, where we do all sorts of artificial intelligence around Samsung Group. You might know us best as the producers of mobile phones and television sets. One of the unique points about Samsung is that we actually do all of our own manufacturing. All of the plants are Samsung owned and operated, so actually most of Samsung Corporation is busy manufacturing those consumer electronics. So that gives us some perspective on intelligent maintenance and operations in at least the factory context. Personally, I used to run my own startup company called Algorithmica, where we serviced mainly the oil and gas and chemicals industries. So that's where I got my field training, if you will, going from oil field to factory, looking after various types of asset. The biggest conversation was always around predictive maintenance there. I ended up publishing a couple of books, which are down below at the screen here, that introduce artificial intelligence and their applications to both power generation and oil and gas in particular. So that gives some breadth with a number of case studies. And if you want to hear more, you're welcome to visit either my LinkedIn page or YouTube channel, where occasionally there is some content. Hopefully it's not too bad. And today I'm going to be happy to address the opportunities and challenges that I see. And I want to point out that, at least from my perspective of 20 years of doing projects like this in the real productive industry, as I said, oil and gas, chemicals, and now manufacturing, the biggest challenge has nothing at all to do with technology or mathematics. The biggest challenge is change management. I have seen 9 projects out of 10 fail and not hit productive use. And the reason in virtually all of those cases is not that the mathematics didn't work, or that the software had a bunch of bugs in it, or that the data was faulty, or that we didn't have the data, or anything like that. It was nothing technological at all. It was quite simple that the people involved didn't want to do it. Mostly it was the end users. Sometimes it was management. Now the end users most of the time don't want to do it because they weren't involved in the process. some boardroom decided to do something. A bunch of mathematicians like me coded up some software, and when it was all done and dusted, there was a meeting to tell the end users, hey, lucky you guys, here's a new tool, go away and use it. And there were always two major issues. One, there were a couple of practicalities that the people like myself just simply didn't know about, right? In real life, you need to have a button that does that, but nobody considered this. So the program was practically not usable, even though the mathematics worked out fine. The other aspect is that people were dissatisfied that they were not taken along for the ride. They were not asked for advice, they weren't asked for their input. And now at the end of the day, when everything is said and done, they were simply ordered, like in the military, to go away and use it. And so there was a lot of psychological resistance. That, in my experience, is the number one and virtually the only real cause of failure for any kind of software technology, whether it be artificial intelligence, machine learning, whether it's predictive maintenance or optimization, to fail in real practice. Now, the potential side, because most projects have so far not been put into production, because upper level management continues largely to talk about, but not to actually implement predictive maintenance and process optimization in the industry. The real potential is the potential that has been there all along, the potential for additional yield, additional efficiencies, less maintenance costs, fewer failures, and so on in productive use. And so the money that has always been promised from these technologies is still to be reaped. So it's a very significant opportunity. And from the software side, we are ready to go. Thank you.
Thank you very much, Patrick, for this introduction to your perspective. And then I'm giving over to Daniel to share his perspective, who has been putting some of the algorithms into production and operation.
Thank you. Thank you, Olga. Thank you for the invitation. Good morning, everybody. Good afternoon, depending on your time zone. A few words about myself. My name is Daniel Nikovski. I'm the group manager of the data analytics group at Mitsubishi Electric Research Labs in Cambridge, Massachusetts. And the objective of my group is to develop and commercialize AI technologies and apply them to the various products that our company, Mitsubishi Electric, is manufacturing. And these are mainly electromechanical devices. So predictive maintenance is a big part of the expectations of users for new technology in this area. My own background is in AI, robotics, machine learning. Again, similar to Patrick, I've worked at big companies and also have had my own startup. And current research interests are in machine learning and optimization. Now, to move on to some challenges and some problems that I see in this area, I think the first and foremost issue in this field is the availability of high quality data. So nowadays, data is very much in vogue. Everybody talks about the value of data, and everybody talks about how data is the new gold or the new oil. And this is certainly true from the point of view of its value. But it's also true from a different point of view, because just like oil and gold, good data is actually very scarce, contrary to what some people might say. And by good data, I mean correctly labeled data. So the availability of high quality data has been, in our practice, the single most important factor for success in industrial data analytics projects. So what opportunities do we have to deal with this problem? So obviously, one of the things that we can do is collect more data, organize it. So Olga, you have been working on that, collecting data sets, making them available. this is a great thing to do. However, from an algorithmic point of view, it is very important to make the best possible use of the little data that we actually have. So if we can make use of unsupervised learning algorithms, that is great. So this is the kind of data that is abundant. And here on the right-hand side, upper right-hand side, there is an example of the use of this kind of data from the HVAC domain. So for an air conditioner, we can fit a relationship between some variables. In this case, it's the superheat of the air conditioner as a function of the inside temperature and the outside temperature. So once we have this relationship, anything that is a deviation from this value signifies a problem with the refrigerant of this system. So for anomaly detection, this is good enough. We can make use of this data. However, if we would like to know whether there's an excessive refrigerant or there is a refrigerant leak, which is a big problem that contributes to greenhouse effects and global warming, and the owners and the vendors of such devices can be fined actually for refrigerant leaks. If we want to know what is going on, we need to have labeled data. Labeling is very difficult. So we need to charge, underfill or overfill the device with refrigerant and be able to create some labeled data. This is very expensive and very difficult. However, in some cases, we might be able to mix unlabeled data for the specific machine and then a generic model for the classification and for diagnostics of systems. So this type of transfer learning across machines, regimes, conditions is very important. If we hope to collect data for every specific model of machine and have enough data to be able to learn a model, this will very likely fail. Another kind of data that we have is weakly supervised data. And this case happens when we have, for example, a operational data collected from a machine that ends up in failure. So clearly at the end of the operation, the machine was in a bad state. At the beginning of the operation, it was in a good state. But we don't know at what point the state changed from good to bad. So we have a generic label. So it ended up badly, but we don't know what part of the data is good and what is bad. There is still some labeling here, but it's not enough. So this is an example of weakly supervised learning. Another type of machine learning algorithm that we can leverage is active learning. So if we make a decision and then we present it to the user and the user tells us, no, this is the wrong decision. The system needs to learn from this, add it to the training example, correct its model so that actually its performance can improve. If it does not, it will no longer be interpreted as an intelligent system. And also integration with simulators, physics engines, sometimes in form of Modelica models, is a very good direction. Recently, there has been really huge advances in some domains, say robotics, thermodynamics. They're great simulators, and calibrating these simulators with physical data is a great opportunity to leverage the physical model and at the same time make good use of data to make the model very precise. And as you can see, all of these developments are under essentially advanced machine learning, which is what I consider the biggest opportunity for this field in the future. Thank you. And maybe we can move on to some questions and the discussion.
Yes, thank you very much to both of you for giving already some directions and giving some thoughts already. So I would like to start with something that Patrick mentioned on his slide. So you mentioned that 9 out of 10 projects actually failing. Can you maybe elaborate if you had any experience with the 1 out of 10? So what went well there and what was the success story behind it?
I do have some experience with the 1. I also have some experience with the other 9. So when I say 9 out of 10, I'm referring really to the projects that make it to the point where the question is asked, shall we put it into productive use? There are, of course, projects that are terminated prior to that. Projects that either turn out to be too expensive or too laborious on the workforce, or that show scientifically that it will just not work out. Those are not included in my 9 out of 10. So by 9 out of 10, I truly mean the decision to be put into productive use was answered in the negative. Sometimes there are financial reasons, but a lot of the time, really, we face that adoption challenge. So convincing humans is a really major challenge. Although, of course, I agree completely with Daniel that we have a number of data challenges as well. So where does it come in? In real industry, of course, we have multiple stakeholders in projects like this. To make it very simple, we have the people who make these things, people like myself and like Daniel. We're obviously invested in this being used, so our opinions are clear. Then we have the, let's say, line managers on the user side. Those people, by necessity, were involved in making the model because those are the people who gave the domain expertise. And this is another one of my pet peeves that I insist on, that you must absolutely have a conversation between the data scientist experts and the domain experts who know this particular piece of equipment, this particular process, or whatever it is that you're modeling. And by necessity, these are different people, right? I've spent 20 years becoming an expert in data science. I don't know refrigerators, right? And this other guy, he has spent 20 years being an expert in refrigerators. I need these two people to speak to each other. Those two stakeholder sides are generally sold on the project, the idea, and wanted to go forward because those two people made the thing. But then you have other stakeholders in the organization. You have senior level management that, other than a couple of pretty PowerPoint presentations, didn't see the rest of the project. And they're mainly involved by funding it. So they need to be convinced based on a business case, which has to be made sufficiently transparent. They don't care, and they shouldn't. They genuinely shouldn't, about the mathematical algorithms that were used or about the data quality that went into it. Who cares? They care about the dollar value at the end of the day. And so someone needs to communicate it to them in that language, which is difficult. And that requires communication skills. So typically at school, we learn how to read, write, and listen. But the most important skill in this context is PowerPoint slides. You have to be able to communicate in the language of PowerPoint, and then also stand up in front of a boardroom and deliver that presentation. That's a new form of language that, unfortunately, at school and at university, nobody is taught, right? So if I may give a hint to the ETH here, teach your students how to write and how to speak PowerPoint. It's incredibly important as a skill out there in the corporate world. And of course, as I said,
maybe a question: how long will PowerPoint survive? How long will it be the language?
Well, of course, I use PowerPoint as in the example of the Microsoft utility. You are free to use any other kind of software tool. But if you let the software tool go, I believe this language is here to stay for good. Because as long as we are human beings, we love to meet each other. We love to sit in one room face to face with each other. And I say this in the irony that I'm not there with you today. So we need something to show, right? In the old days, philosophy lectures were read from a written speech. I've sat through some of those. Never all the way. I usually fell asleep towards the end. And that is the reason why we no longer do this, right? We no longer write our speeches and read them. We speak verbatim, like I'm speaking to you now, generally with visual aids. And that's where the PowerPoint presentation comes in. That's where the diagram comes in. PowerPoint slides are not to be filled with words. They're to be filled with diagrams and pictures. That's the real language here, which is why it takes a very long time to make a presentation. Generally, to give a 20-minute presentation takes me 2 days to paint the slides. And you have to be prepared for that. Anyway, I digress. The fourth group of stakeholders are the end users, and they're the most important because they have to end up using it, and they're generally ignored. So that's what I refer to.
Okay, thank you very much, Patrick, for this answering or elaboration of the point about the one project that is successful. How about you, Daniel? I think you were in the position where you needed to convince your product managers probably, because at the end you're developing something mainly for your customers who will be using it. So it's not just convincing the product managers, but also the customers to use the product. Maybe you can elaborate also on that and elaborate also which qualities the successful projects have.
Right. So I agree very much with what Patrick was saying. And I have to say that the success ratio in our company is about the same. It's certainly not above, 1 in 10. So many projects fail for all kinds of reasons. And of course, good communication between the stakeholders is very important. And removing misunderstandings as quickly as possible is essential. I'm very familiar with the process that Patrick was describing of explaining ideas in PowerPoint. We call it PowerPoint engineering in our company, and it's, for many people, it's a full-time job. It is very important. But one project I would point out that worked out really well. The reason was that there weren't that many people involved in the decision process. So it was the diagnostics of motors for our compressors in air conditioners in one of our factories. And it was a big success for several reasons. So first, we had a single person who was an expert in the area and could also have access to the people in the field and could collect data. So again, I would stress the importance of data. And this data was not collected specifically for this project. It was simply at the end of the inspection line, there was already a person who was inspecting devices and was labeling them good or not good. So we were essentially piggybacking on this existing data set. So this is a very good way to have a project succeed if you do not have to arrange data to be collected just for this project. Right? Use existing data as much as possible. If you think about what Amazon did, for example, for their recommendation engine, they did not collect data from their users. Do you like this product? Do you like that product? In order to be able to collect this data. They were simply using their sales data, piggybacking on that. And then their recommendation engine became a huge success. Same thing with Netflix about their movies. At one point, they were actually asking people to rate movies. But in general, it's just simply by what you watch and your viewing habits that they can derive what is going on. So this was a very important lesson. Try to piggyback on existing efforts, on existing projects. And then, of course, the relatively small number of people involved, right? So there was nobody actually in the internal central R&D organization. We were talking directly to the people in the factory. So if you can cut some intermediaries, it actually always helps. It always helps. So this was happily deployed in most factories and is replacing workers who were doing the diagnostics themselves by listening to these devices. And all the workers are retiring. So essentially we are replacing them with this technology. So again, the availability of data and the smaller number of stakeholders are critical factors for success.
Thank you very much also to you for elaborating this success story. So there are two related questions from the audience, and both of them are related to data and to interpretability. So the question is, when you're employing AI in real world, correct interpretation of data also matters. So how do you see that? And related to that is, so do you see that explainable AI will help to get those projects more acceptability, since they're providing a bit more explainability and also possibly trust to the users at the end? So how do you see that in your projects, and how do you see that developing also for future applications?
Well, this is always an issue, whether the learned model or the derived decision is explainable. So I would say there are applications where people are completely happy to get a prediction or get a decision without necessarily understanding why it was received. On the other hand, if this decision can be explained, especially in safety critical applications, this would be very useful. So in the field of predictive maintenance and diagnostics, it is actually very useful when there is an anomaly detected to explain where this anomaly is. So there are good algorithms where, for example, you're scanning a very high dimensional time series that comes from a large IoT installation. And then when there is an anomaly, of course, it could be a contextual anomaly. Some of these time series is anomalous in the context of others. If this decision can be extracted and presented to users, it is very helpful, because it's not only convinces them that yes, there is an anomaly, but it gives them a plan on how to resolve the potential issue. And again, the answer is algorithmic. There are algorithms for causal analysis. There are algorithms also for analysis of the which features in a predictive model are valuable. The LIME algorithm comes to mind, and there's active work in this area. So I would say some fairly major advances have been made in the last 10 years.
How about you, Patrick? Did you have any experience with that? And does it really improve the trust and also the acceptance of the projects?
Yeah, so I completely agree with Daniel. In fact, what he said is the software tool that my previous company made exactly to explain the predictive maintenance phenomena, where it's of course very important for the reasons he mentioned that we get an explanation. I think in many applications, it is very important to be told why, or to be given some reason and into context of what's going on. And explainable AI alongside ethical AI are the two big research topics right now at the moment that everybody's going off on. Even with visual AI, computer vision, there are explainable systems available now. So that if if in an industrial context you send a drone up and you take a photograph, or you take a picture in your manufacturing line and there's something wrong, there are explainable systems that will tell you where in the picture the mistake is, or it will give you a series of typical pictures and what the difference is between the one you're dealing with and those reference cases, to allow you to understand why the AI has chosen to point that one out. And I think especially in vision, there is a big frontier here for explainability, to allow people to understand what's going on. And then, of course, to draw the right conclusions. But we typically then need to act on this, and maintenance is always the prime thing. But process optimization is the other side of the coin, right? If I'm going to make the decision to change a set point in an industrial process, maybe to the extreme of my comfort zone, perhaps even outside of the comfort zone I've been living in for the last years upon years, then I need to be told why, that optimization algorithm is trying to get me to do that. And typically in an industrial context, every decision I make is a multi-million-dollar risk, right? If I ignore the maintenance alarm, I'm just possibly incurring a failure. If I respond to the maintenance alarm, I'm shutting down the equipment. Either way, I'm screwed, kind of, financially speaking. Yeah, no matter if I say shut it down or keep it going, I'm going to lose a lot of money. The question is which one is better or worse, right? So explainability in the industrial context, I think, is going to be crucial.
Thank you very much also for elaborating that. So there is a question particularly to Daniel. The best part is the one that does not, which does not exist, but its function is executed. Why not incorporate sensing in parts design and not attach a sensor?
Well, the issue is cost, right? So the issue is always cost, and big vendors of equipment are very, very conscious about cost. So one example could be the air conditioners. We worked for 7 years on the new controller of the room air conditioner, and we wanted to have an additional sensor, which cost temperature sensors 500 yen. This is less than $5. And we proposed to install it, and it was as if our intention was to bankrupt the company. That was the reaction, right? So you need to explain really, really well why you need an extra sensor. So if you can actually analyze the existing data and create virtual sensors, even if it takes a longer time in R&D, this is a very welcome development for a manufacturer of a large series of equipment. So these air conditioners sell in the hundreds of thousands. So adding an extra sensor is not a good thing. However, of course, if you can get significant benefit, and if you can explain it to stakeholders, to the people in the factories, again, using large amounts of PowerPoint, as Patrick explained, then that might be a good way to go.
So both of you are referring to making or convincing the stakeholders to provide budget to finance the specific project. But one of the challenges is also to make the business case and to really calculate the numbers, because if you have the right numbers, it could be even the wrong PowerPoint, it would still work. But isn't it a problem for our field that actually we are trying to calculate something that we hope that will never happen? And how do you deal with that? Because actually you're trying to put into something, or the benefit is something that is supposed not to happen. So what are the costs of the consequences? And what is then the cost that you would like to put in order to prevent that something that will never happen or is supposed to never happen? So how do you deal with that? And also in terms of convincing the stakeholders who will give the money for the project?
Indeed, that's the main challenge, because anything related to maintenance, you're effectively selling insurance. You're not making the process any better. You indeed are trying to prevent something that shouldn't happen. So what's the upside? In many companies, you will have to look a little hard to find real costly failures of the past. There might be 5 years ago, this thing exploded and cost $50 million to repair. And if you take that example as a base case, or the 2 or 3 other examples that you can find as base cases, people will start arguing with you. In that specific example, it was this and that and the other that was responsible, and not what your algorithm will solve. And they will nitpick to an extreme about that. On the other hand, if you focus on the less costly, much more frequent events, and you say, okay, in the last year, you had 1,000 events that cost $2,000, sum them all up. then they will also nitpick, right? But it's very cheap and very small and very quick, and who cares? Insurance salesmen are never very popular, and that's one of the biggest problems of predictive maintenance that I've seen. I turn into an insurance salesman, but essentially what we need to point out is that the technology does work, and so in the future the cases of failures, both the many that are cheap and the few that are disastrous, they will go down. They will not go down to zero, but they will go down. And so there is a business case. Now, it's a matter of belief now, and genuinely belief, right? Bayesian statistics. How many of these are you going to eradicate? And you can do a kind of best, average, worst case scenario planning to your senior leadership. They're used to that, right? These three scenarios. And make different assumptions as to how good your algorithm is going to be. So you can make a business case like that. But if it isn't maintenance, then in fact, you are not the insurance salesman. You are directly selling profitability, because if your AI is able to make the process better, then you are selling things like efficiency, like less CO2, like more yield. And those things have a direct and immediate dollar value. And then it becomes a lot easier to convince people.
Thanks for sharing that. It's an interesting perspective to consider it as an insurance seller. How about you, Daniel? How do you calculate your insurance?
Well, I completely agree with what Patrick is saying in terms of how this works. But also I have to say that in the case of our company, it is relatively easy to sell this insurance because of the reputation of the company, right? So let's take as an example a different business of the company, elevators, of which Mitsubishi Electric has about 10% worldwide share. So in that case, the customers are very, very happy to buy a maintenance contract, right? Because of the known high quality of the product, and because of the peace of mind that this gives them. Now, the revenue part, the sales part, is taken care of, which is what Patrick was referring as a very difficult sales job, but it's taken care of. And then from then on, whatever technologies we can implement to reduce the cost of executing these contracts is pure profit for the company. That's why it's very easy sell in our company. It's really very easy sell. So we've been working on technologies for monitoring remotely the operation of elevators, also for predicting the likely failure, for optimizing the logistics, the supply chain of parts, so that the parts are basically ready as soon as something fails, or just before it fails so that we can replace it. In addition, optimizing the technicians, the crews that go and do the inspections. And in many cases, some of these inspections have to be done every 3 months. Well, definitely inspections need to be done every year because that's the law. But in some cases, some of these inspections are done every 3 months. If we can reduce the number of these inspections, because we know that the part is performing well, or we know that the remaining useful life is a lot more than that, and we can save the trip of the technician, that's pure profit for the company. It's a very easy sell.
Yeah, I think you've made a very beautiful and very important point here, namely that artificial intelligence allows you to drive a new business model, right? You're selling a kind of old style maintenance contract, and you're doing the AI internally, which means you don't have to sell the AI to anybody. You're keeping it in-house, you're making the profit on your own, as opposed to going to the customer and saying, buy this new shiny maintenance contract, there's AI in it, right?
Right.
That's not gonna fly.
Right.
I love it. Yeah, this is good.
But you actually mentioned quite an important point, Patrick, that of the business models. And you had your own company where you were actually trying to sell this type of service products, possibly to operators, but also to manufacturers. now you are developing this in-house. Also, Daniel is developing this in-house and providing it to the operators. But how do you see this landscape evolving? Because there are several stakeholders who are actually developing similar things that are providing similar type of service or similar type of technology. And kind of everyone is then competing to do that, or to that their tool is deployed. So maybe, Patrick, how were you dealing with that when you were startup, and how are you dealing now with that, and how do you see that evolving over time, because they're quite contradicting interests?
Well, I mean, of course, in every industry, there's competition. And if you think that you are unique in your particular area of the world, you're either wrong or you will be wrong soon. So you have to deal with the fact that other people do similar things. Now, I think in our case, here, people do specialize. So for example, I specialized in oil and gas in my previous company, and that's where I had domain expertise, right? So if you came to me with, I don't know, a shoe manufacturing plant, then I would have had nothing to say. And there are other people who specialize in other types of manufacturing. And same now here at Samsung, we do specialize in certain areas. So for example, I now specialize mostly in medical imaging, diagnosing cancer based on MRIs and CTs and X-rays and things like that. And so I've acquired a little bit of, by now only a little bit, but some domain expertise in that area because I talk to the doctors. You can never cover the entire range of use cases with a single product and a single team of people, simply because they don't have the knowledge over everything. They cannot, and more importantly, they don't have the contacts. You have to invest a lot of time and effort to getting to know the right people at all the right companies around the world, and talking to them, developing some kind of friendly relationships. And so by necessity, you specialize. And so that if there are 10 companies that do seemingly the same thing, they're probably actually not doing the same thing, because they're either doing it in different industries for different machineries, different contexts. But ultimately, yes, they compete. And then you can pick. One thing is to pick on expertise, other is to pick on price or offering. I find most of the time, actually, the real competitive edge to the financial decision maker is often the look of the user interface of the computer software.
How about you, Daniel? How are you dealing with these new emerging startups that are trying to sell something similar, probably as you are?
Well, in terms of competing, right? So, you know, the saying in the startup world, in order to displace an incumbent company, the startup needs to have a product that's at least 3 times as good or at least 3 times as cheap, right? So there is a huge bar for these startups to compete. It's relatively, we're not seeing a whole lot of pressure from startups. Now, if we look at them as possible suppliers of technology, of course, there are interesting solutions here and there. But by and large, the main source of technology for us are universities. So many startups are trying to convince customers that they have some kind of a secret sauce and they've done something great. And maybe sometimes they do. But the thing is, a much bigger source of technology are universities. So the innovation engines of the United States, Europe, and Japan are extremely strong. There is a constant string of innovations, just keeping up with them, just acquiring these innovations and putting them into product takes a lot of time. And many of these university organizations do not have very restrictive terms. They're very happy. They're, in many cases, taxpayer supported. And we are paying these taxes as big corporations in terms of our income taxes, right? So it's a very nice ecosystem. And I would say the startups right now are not necessarily such a big part of it. So the main flow of technologies, universities to big corporations to end users.
Thank you very much. Unfortunately, we're really coming to an end. Actually, we're already at the end, but I would still like to ask you one last question. And the question is, how do you see the field of intelligent maintenance, but also operation evolve over the next 20 years? And where do you see it? So what are possibly the biggest developments that you see and that are the most promising? I don't know who would like to start.
I mean, I see the biggest potential here in the explainability, like we discussed earlier. So far, most of the tools that I'm aware of are simply alerting tools that there is something wrong now or that there will be something wrong in the near future, but they typically don't explain exactly what it is, where it is, or why it's happening. And I think those three questions are really the things that need answering and that will do in the near future. Then, of course, the follow-on is the interfacing to all the tools that happen later, like who's going to do it, when are they going to go, what tools do they need to take with them, what spare parts need to be ordered in order to be able to do that. Those are the kind of integration tools with, you know, our most popular software is SAP and such, to make it all really practical.
Thank you very much. How about you, Daniel?
So I think the big development in the next 10, 20 years will be autonomy. So currently there is a lot of human effort involved in maintenance and in prognostics and essentially in minding the machines. So in the next 10 to 20 years, everything will be connected to the internet. And this is happening now. It wasn't the case even 10 years ago. In the early days of the internet, people said, oh, your refrigerator will be on the internet and it will do wonderful things, but nobody could explain what business your refrigerator had to be on the internet. However, intelligent maintenance is one such killer application. And this is true about every possible electromechanical product. So this is happening with our air conditioners, which again, 10 years ago, barely any of them were connected, except the big floor level models. Now all of these devices will be connected. All elevators will be connected. All cars will be connected. So the car's self-diagnostics and self-inspection will be ongoing all the time. There will be no annual car inspections. Doesn't make sense, right? The car will be inspected all the time, completely precisely, will be connected all the time, and all maintenance will be done completely autonomously. And maybe the way things are going, the car will also drive itself to the repair garage to have itself fixed. So autonomy, I think it will be the big development.
Thank you very much also for this insight. And we could be discussing for hours, actually. And it would be nice to have you here and to continue discussing with you over the apéro afterwards, because you gave such nice thoughts and such nice starting points for discussions. We hope to have you one day here also to continue the discussions. But thank you very much for joining so early in the morning, for you, Patrick. And thank you very much for sharing your knowledge, but also your experience in this field.
It was a pleasure to be here. Thank you for inviting me.
Thank you for the invitation, Olga. Thank you.